How do stars form, you say? Oh, that's not what you said. Too bad. We often say space is a vacuum, but gas and dust particles are present, if thinly spread. This is called the interstellar medium. This can be distributed through events such as supernova, resulting in areas with more or less gas than average. While this doesn't always have a huge enough effect, occasionally enough gas can collect to result in it collapsing due to gravity. It begins to heat up as temperature is the measure of average kinetic energy of particles, which increases because the particles are forced into smaller and smaller spaces. As pressure is proportional to temperature, the higher the temperature, the more the pressure. Once this pressure equals gravity, the star reaches hydrostatic equilibrium. At this massive temperature, nuclear fusion starts, where the hydrogen atoms collide with each other, forming helium and releasing energy in the process, and thus a star is born. These early stars, or protostars, are surrounded by what looks like cocoons of dust, which indicate that the stars only recently have ignited, as these cocoons are predicted to disperse quickly and are found in dense cores of molecular clouds. Protostars exhibit strong winds, producing a bipolar flow, expelling two jets of matter in the direction perpendicular to the disk, as shown by my scribbles. As the protostellar wind destroys the disk, the wind begins to flow equally in all directions. While a protostar is not initially hot enough to result in fusion, many of them will eventually start fusion as they move towards the main sequence. Bum, bum, bum. Sometimes there is not enough material present and a brown dwarf forms, which often has many similar properties to large gas giants in mass, size, and temperature. As these will not result in fusion due to their low temperatures, we can just push those aside and focus on the real stars. Let's talk about the main sequence and the HR diagram for a second. An HR diagram, short for Hertzsprung-Russell diagram, compares a star's temperature to its luminosity. It's important when using this diagram to remember that the luminosity scale is a logarithmic scale in this case. When plotting tons of stars on this diagram, it reveals the life cycle of stars. Although we can only see a snapshot of the lifetime of one star, using thousands of stars reveals trends that correspond to different points in the life cycle of a star as a whole. From this diagram, we can determine much information on the life cycle of stars. Stars spend much of their lives on the main sequence in the core hydrogen burning phase of stellar evolution, and leave the main sequence when hydrogen in their cores is exhausted. The Sun is about halfway through its main sequence lifetime and will burn out in 5 billion years. Low-mass stars evolve more slowly and high-mass stars much faster than this, as lower-mass stars burn fuel at a much slower rate than higher-mass stars. But when the fusion in the core ceases, as there is not enough hydrogen left to fuse, helium is still too cool to fuse into anything heavier. These main sequence stars make up around 90% of the universe's stellar population, ranging in luminosity, color, and size from 1/10 to 200 times the Sun's mass, and live for millions to billions of years. When this central fire ceases, the core is unable to support itself against its own gravity and begins to shrink. Then the star starts burning the hydrogen shell around the helium. The star becomes much brighter and expands at this point. A star with similar mass to the Sun would move off the main sequence to the subgiant group and then up to the red giant group. Eventually, the core reaches a point where the helium core begins to fuse and form carbon. However, due to electron degeneracy, the fact that electrons can only be compressed so much, the helium fusion does not release usable energy. As a result, a non-burning carbon core is created. It shrinks and heats up the nearest layer. Low-mass stars never become hot enough to fuse carbon. It ascends the asymptotic giant branch, where it once again becomes a red giant before finally blowing away its envelope, forming a planetary nebula. Stars in binary systems evolve differently due to their gravitational interactions. As a binary star becomes a red giant, it may overflow its Roche lobe, or an area where orbiting material is gravitationally bound to the star. This results in gas flowing to its companion and will result in a binary star nova. Stellar explosions! Woo! A nova is a star that suddenly increases in brightness and fades back to its normal state over a period of months, as a result of a white dwarf draining material from its companion star. The gas spirals into an accretion disk around the white dwarf, becoming hot enough for the white dwarf to burn explosively, causing a temporary increase in the dwarf's luminosity. Stars more than 8 solar masses form heavier and heavier elements in a rapidly increasing rate, stopping at iron, which can neither be fused nor split to form energy. As a star gains more iron mass, it eventually collapses under gravity, where the iron begins to split into neutrons and protons, the protons combining with electrons to produce neutrons. The star becomes so dense that the neutrons are effectively touching, resulting in a core collapse supernova. All elements heavier than helium are formed by nuclear reactions in the core of evolved stars. Dun dun dun. A core collapse supernova leaves behind a remnant, an ultra-compressed ball of material known as a neutron star. These are extremely dense, hot at formation, strongly magnetized and rapidly rotating. They often cool down and lose their magnetism and slow down as they age. Because neutrons are magnetized and rotating, they send regular bursts of energy into space, produced by charged particles confined in the magnetic fields. The beams seen from Earth are called a pulsar, and the pulsar period, or period that the signals are received, is the rotation period of the neutron star. Because the pulse is beamed into space and the neutron star slows down as they age, not all neutron stars are pulsars. A neutron star in a close binary system can draw material from its companion, forming an accretion disk. The material in the disk heats up before it reaches the neutron star, making the disk a strong source of X-rays. As gas builds up on the surface, the star becomes hot enough to fuse hydrogen. When hydrogen burns here, it does so explosively. The rapid rotation of the inner part of the accretion disk causes the neutron star to spin faster, resulting in millisecond pulsars. Gamma ray bursts are energetic bursts of gamma rays observed once per day, which may be the violent result of a merger of neutron stars in a distant binary system. Gravity is a warping of space-time as a result of mass and particles move in curved paths. The upper mass of a neutron star is 3 solar masses, after which it becomes a black hole. Very massive stars, after a supernova, become black holes. The conditions in and near a black hole can be described using the theory of general relativity. The radius at which the escape speed equals the speed of light is the Schwarzschild radius, at which point there is an event horizon, a point where nothing can escape, not even life. Light leaving an object falling into a black hole would be subject to redshift as it climbed out of the black hole's field. Near a black hole, a noticeable amount of time dilation would occur, where an object falling into a black hole would seem to freeze just before the event horizon from an outside viewpoint. Conversely, for the object falling into the black hole's perspective, the outside universe would seem to speed up and get bluer. Once an object is massive enough to have an event horizon, it is massive enough to reach a singularity, at which point both the gravitational field and the density is infinite. At this point, the laws of physics appear to break down, and anything on the inside would be unable to interact with the outside world. However, on the way in, matter can form an accretion disk and emit X-rays. So long, and thanks for the fish!